Good evening, everybody. I hope you're all well. This evening, Michael Poxon has been interested in astronomy since about the age of 5, even though his degree is in linguistics. A little confusing, but you can always explain. And especially variable stars. He independently discovered Nova Cygni in 1975 while doing his A-levels, being a member of the American Association of Variable Star Observers, an amateur professional body affiliated to Harvard University. His special interest is in young variable stars, and he runs the Young Stellar Objects section at the AAVSO. In 2002, he was awarded a NASA grant to participate in an astrophysics conference in the Big Island of Hawaii, and has written a book on astronomy with binoculars. So can you all please put your hands together in a mixed way and welcome Michael Poxon.
Thank you for that lovely resounding introduction. I think you'll all be pleased to know there are no variable stars tonight. We've got a different sort of star to talk about this time, and they are called runaway stars. Probably not a lot of people have heard of runaway stars. I really hadn't heard too much about them until I started working on the paper, which would eventually be published somewhere, probably the Journal of the AAVSO. Yeah, and I found out quite a lot of interesting facts in that direction. So I'll just see if we can screen share properly. Yes, we can. So I'm going to kick off by saying what we're not talking about. We're not going to be talking about what are called hypervelocity stars. These are actually sort of a more extreme form of the kind of stars I'm going to be talking about tonight, because these hypervelocity stars are stars that have been actually kicked out, as it were, of their home galaxies, usually by being spun out by a black hole. We're not going to be quite as exotic as that, but runaway stars are interesting from a couple of points of view, because they tell us about the two extremes of a star's life. Because you can get various runaway stars, A, as a result of star formation, and B, as a result of star destruction. So we've kind of got the wombed tomb, as Dylan Thomas would call it. You see, that's the linguistics coming out, see, and the poetry. Never mind the astronomy. Right, I just want to kick off with a little bit of background information. What we're going to be talking about are stars that appear to move across the sky. This is obviously over a long period of time, which we'll see in a minute. Stars that move across the sky faster than normal stars. Normal stars, like the sun, travel through the galaxy at something like 20 kilometers a second, which I know by everyday standards is really, really fast. But you have to bear in mind that the stars, even the small stars, are very, very big things. So 20 kilometers a second with reference to the size of a star is actually pretty slow, and the sun is one of those. It's a fairly normal star moving at a fairly normal speed. What we're really going to be talking about is the motion of the star across the sky. That's this distance here. Now, as you can see, this is a triangle, and this triangle is composed of two other parts, one of which is what we call the radial velocity, which is how far the star is coming towards us or away from us. Now, obviously, not all stars are coming directly towards us or directly away from us. So the other motion we have to bear in mind is the actual real physical motion of the star, which is this one. Whoops, sorry, accidentally went to the wrong slide. Which is this motion, and the motion across the sky is the one that we're going to be looking at. Okay, this is called proper motion, and there are various high proper motion stars, but there are various reasons why they have this high proper motion. And this is measured in an angle, which is the angle we see here. Okay, this is the speed, but this is the angle, and it's really the angle that we're talking about, because obviously the angle depends on the speed and the distance. I just want to, there we go. So this is just a little graphic showing how the stars in the plough appear to move. This is over a period of about 400,000 years. Now, as you can see here, they're okay, they're moving, but they're not really moving all that fast. And what's also remarkable is the 5 stars in the middle, that's beta, gamma, delta, epsilon, and zeta. Zeta is, of course, Mizar, the famous double star. They are not really moving very much, or certainly not as much as this one, which is alpha, and this one, which is eta. And the reason for this is because the 5 stars in the middle were all formed in the same part of the sky at the same time, and they are part of what's called a moving group. In recent years, with satellites such as Gaia and Hipparcos, which I actually worked on, we've now amassed a lot of information of the motion and the position of stars. And these 5 stars in the middle, as I said, they got all created at the same time in the same part of space. So basically, all the gravitational influence of them have been the same over that period of time. These 2 stars, however, were formed in some other part of the galaxy. They just happen these days to form part of, of the plough. Something else that's actually interesting that I haven't sort of made a note of here is quite a lot of the stars in the spring sky, several of the stars in the constellation of Lynx and Leo Minor are actually all part of the same moving group as these 5 stars in the middle. So it's, it's on a really large scale. So you can see the proper motions of these stars are actually quite slow. And there's a reason why it appears so slow. And that is because we're all in it together. That everyone's heard that phrase quite a lot over the past few months. Yes, we're all spinning around the galaxy, and obviously most of the stars that we can see at night are relatively close. So, we're kind of moving more or less as a block, really, over a human lifetime. That's why the positions of the stars over a human lifetime don't appear to change very much. And you need to look at hundreds and thousands of years to see any detectable motion. That is, with the naked eye. Obviously, if you're zooming in on a very tiny area of sky, then the motion is a bit more evident. But even so, you can't really tell much of a difference from one year to the next. You need lots and lots of years. But I just want to draw your attention at this moment to a little bit of the constellation of Ophiuchus. For those of you who aren't familiar with the constellations, Hercules is probably up to, it's way up to the top right hand of your screens, but actually way off the screen. The brightest star in Ophiuchus, which is Alpha Ophiuchi, it's sort of near the top of your screen. And you get a little line down from that to beta and gamma. There's a nice little open cluster here called IC4665, which is brilliant in a pair of binoculars. It's too big for telescopes, but it's great in a pair of binoculars. Anyway, to return to the subject in hand, there are lines attached to some of these stars, and the lines show how much the stars appear to move over a period of 5,000 years. So as you can see, they don't appear to move very much, even over 5,000 years. Beta Ophiuchi here has got a tiny little line attached to it, which probably means it's a very, very long way away. So even over 5,000 years, it doesn't appear to move very much. So it's got a very small proper motion. This star here, it's got a very long line attached to it. So we can presume that's either a fast moving star or it's a close at hand star. Now, the most remarkable line in the picture is this one, which goes right off the chart. The reason why that line is going off the chart is because that line refers to a 9th magnitude star, which is about here. called Munich 15040. Now that's a weird name for a star, isn't it? Most people know it as Barnard star. And why Barnard star is so famous is not only because it appears to move very quickly, but because it's the second closest star to the sun. It's only 6 light years away. So this isn't necessarily a fast moving star. It's just a star that appears to move fast because it's very close at hand, astronomically speaking, obviously. But no, I just want to return to this little T, or if you're into Greek, lambda-shaped group of stars here. These are all 4th magnitude stars, and it's strange, of course, this little group of 4th magnitude stars actually used to be a completely separate constellation. It was called Taurus Poniatowskii. I think we're safer without Taurus Poniatowskii for the moment. It's a bit of a mouthful, isn't it? But this star here, 70 Ophiuchi, is famous mainly for being a really lovely double star. You can split it in a small telescope, and we know that the 2 stars are physically associated with each other because we can see their proper motion lines here. They diverge from the same place and they're going in more or less the same direction. So we're fairly sure that the 2 stars that make up this double are actually, they are going round each other. They are physically associated. If you look at it with the telescope, they're meant to be, I think, yellow and purple, which is a case of what's called complementary colouring. The star isn't really purple; it just appears to look purple because it's near a bright yellow star, and that makes the white star borrow some of the colour that the other star hasn't got. And the opposite colour to yellow is purple, which is why the companion appears to look purple. Anyway, back to proper motions. The other reason why these lines are quite long is again because 70 Ophiuchi is a fairly close star to the solar system. I think it's about 16 light years away, about the same distance as Altair is, in fact. So again, that's why these lines are long, not necessarily because the star is moving fast, but because it's close to us, and so it appears to move fast. But I want to come now to actual runaway stars, stars that really are moving fast and not just appearing to. And as I said in the introduction, there are basically 2 causes of runaway stars. One is when the stars are born. Stars are born out of giant clouds of gas and dust, some of which are the leftovers from previous supernovae, for example. The majority of the stars in the galaxy are actually not single stars like the Sun. The sort of common way that stars form is usually in 2s. That's why we tend to get more double stars than single stars. Not much more. It's about sort of 60-40. So, okay, the Sun is in a minority, but it's a fairly big minority. When stars are in the process of forming, because they're condensing out of the gas cloud, the gas in the cloud isn't motionless. It's swirling around because of gravitational attractions of other nearby bodies, for instance, other forming stars, for instance, which can be very, very massive sometimes. So there's a lot of stuff going on when stars are being born. And if we have a non-single star, or sometimes a very massive single star, it's fast rotation, which is a corollary of the fact that the gas is swirling around. Fast rotation is a signature of youth as far as stars are concerned. So basically, the faster a star is going around, you can usually bet it's a fairly young star. So obviously, under those circumstances, the way is open for the case where you have a star that's rotating so fast that part of the mass of the forming star, or even sometimes the smaller component of a forming double star, it's rather like if you put a weight on a piece of string and swing the string around your head and then let go of it, the weight flies off. Well, something similar happens when stars are being born, and that's our runaway star being caused at star birth. The second reason, and the really interesting reason for runaway stars, is as a result of a supernova explosion. In a supernova explosion where you have a type 1, which is a supernova that's caused by a too massive white dwarf. Of course, white dwarfs, for various complicated quantum physical reasons that I've got no intention of going into at the moment, can only take so much mass. And if that white dwarf is in a double star system, which is what a type 1 supernova is by definition, then as it's a more massive star, it will be sucking material off its companion, which is obviously a bigger, but not as massive. And once the mass of a white dwarf exceeds about roughly 1.5 times that of the sun, that's when we have our supernova. And obviously the companion star, of course, there can be more than 2 stars in the system, but let's just take a really simple example where we've got a double star and the white dwarf goes supernova. The actual shock of the supernova can send the star, or sometimes several stars, as we'll see shortly, go flying off into space. So that's our second cause of runaway stars. And I can't at the moment see the arrow. Ah, there we are. Now, I know we're in the middle of summer, but I want to take you back to winter because we're going to start with Orion. Everybody knows Orion. There's Betelgeuse, there's Rigel, there's the Belt. Great Orion Nebula is there. You take the Belt stars up, you come to Aldebaran. Take the Belt stars down, you come to Sirius. And here's the winter triangle: Betelgeuse, Sirius, Procyon. There we go. There's Capella, which is right above you in the middle of winter. I don't want to look at these bright stars. I want to look at 3 5th magnitude stars. They're actually all the same brightness. They're all about magnitude 5.5. So if you've got a really dark sky and a decent pair of eyes, you can just about see them with the naked eye if you know where to look. These 3 stars are all very similar to each other. They're all very, very massive, very, very hot, and they're all about 1,000 light years away. The reason for this will become evident in a minute. Our first one is a star called 53 Arietis, obviously in Aries. The second one I want to look at is a star that theoretically, I mean, we can probably see it from Norfolk. You probably can't see it from a little bit further north. In the southern constellation, thought of as a southern constellation of Columba, the dove. Okay, we've got Orion here. Underneath Orion, we've got Lepus, the hare, and underneath Lepus, we've got Columba, the dove. And this little 5th magnitude star here, Mu Columbi, is the second star that I want to talk about. The third one is a star that some of you might have heard of because it's a favourite object of people who like imaging, because it's actually ploughing into a nebula called the Flaming Star Nebula. It's an Auriga, and the star is called A Aurigi. Now, the name will tell you it's a variable star, but I'm not going to talk about variable stars at the moment. It's not a particularly interesting variable star if you're a visual observer. It doesn't change in brightness that much. But the interesting thing about it is, as I said, it's actually ploughing into a nebula, because this whole area here is just full of gaseous nebulae, and this one happens to be ploughing into one of them, and it's causing it to shine. Now, we obviously know how fast these stars are moving, you know, because we've sort of tracked them over the years. They were probably originally photographed at the turn of the 20th century, maybe a little bit earlier. Photographs and surveys that have taken place since then have shown that they're moving much faster than all the other stars around them. So this is how we discovered these 3 stars are runaways. If we take the directions back and the speeds back, they all appear to converge about here. Now, this is a very interesting place for 3 separate stars to converge, because, of course, this is the center of what's called Barnard's loop, which we'll look at in a few minutes. Barnard's loop is the remnant almost certainly of a supernova that exploded roughly in this area. And by taking these lines back, we can show that these three stars were actually flung out in three different directions by the supernova explosion, which happened so roughly between 2 and 3 million years ago. No, the supernova that caused this would have been extremely bright. I'll come back to that in a few minutes. But this is an example of three runaway stars being caused by a supernova. Here's Barnard's loop, and as you can see, if you can think of it as a circle, there are various reasons why we can't see the other bit of it. But trust me, the actual sort of full circle is actually there. It's just that there's a bit of gas and dust in the way, so so we can't see it. And if you look carefully at the sector of the circle, it is indeed centered about here, and that just goes to prove, because this is an expanding shell of gas. Well, it doesn't prove 100%, but it very, very strongly suggests that there was a supernova here, and this is the expanding supernova remnant. And those three stars that we were just looking at were indeed flung out by the supernova. Now, there's a really interesting little question that I'll pose right at the end, but it's worth pointing out that I was actually doing the calculation today. We know how sort of roughly how luminous a type 1 supernova is. And I was calculating if it was a standard supernova of its type, then the magnitude of it when it exploded would have been at least, this is a very conservative figure, it was almost certainly brighter, at least magnitude -10. So you're talking about something more or less as bright as the full moon, but concentrated into a point. It was obviously visible during daylight. And this area is still, as you probably know, it's still an area of very, very high star formation. The Orion Nebula is probably a bit of the debris of the supernova, as are all the other nebulae that scatter around here. Here is the Witch Head Nebula. Here you've got the Horsehead coming down, just about make out the Horsehead, but not going to bother if you can't. The other thing worth actually noting about the constellation of Orion is it's what you might call a real constellation, in that most of the bright stars in it are actually physically associated with each other. They're all roughly 1,000, 1,200 light years away, apart, of course, from our friend here, Betelgeuse, which is only about half that distance away. It just happens to lie, in the same line of sight, and it makes a nice pattern anyway. You actually have a completely separate area of star formation up here. This star is called Lambda Orionis, and it's actually a special area of the sky which is called Orion T1, because it's forming lots of stars about the mass of the sun, which when they're born are variable stars, thank you, and are called T Tauri stars. Hence, areas where you get lots of T Tauri stars made are just called T regions. This is one of them. Obviously, Orion Nebula is another one. Here's Flaming Star Nebula, and here is A Aurigae. And as you can see, it's a bright star in the neighbourhood, and it's the star that's actually making all this nebulosity shine, because it's very hot, it's very energetic, it's pumping out lots of very sort of short-wave radiation, which is making the gas in the nebula glow. All those three stars that we looked at are very, very hot stars. They're all of spectrum type, what's called O, which means their surface temperature is probably in excess of 30,000 degrees. So very, very hot stars. Now, so far, I've been talking about runaway stars in our own galaxy, close at hand, but there are some galaxies which are relatively close. This one is the Large Magellanic Cloud, which, even though it's called a cloud, we obviously know now is a separate galaxy. This is a star with a romantic name of R144. It's actually a pair of stars. The system together is about 1 million times as luminous as the sun. So again, both of these stars are very, very hot. They're even hotter than the stars we looked at just now, 45,000 degrees. And here's the famous Tarantula Nebula, which is where they were ejected from. Now, it's quite possible that the Tarantula Nebula here is itself a supernova remnant. There are lots and lots of very, very hot, very, very massive, very, very powerful stars in the process of being formed here in this cluster called R136. They are very, very young stars, you know, as stars go, maybe less than 1 million years old, which probably means that, you know, that they're only just becoming bona fide stars. But we're not exactly sure what happened there. It was almost certainly supernova, because there's really no other way this star could have been flung out. The distance from the cluster is 4 arc minutes. Now you might think, 4 arc minutes, that's not very much. That's 1/15th of 1 degree, and the pointers in the flower are 5 degrees apart. So that's a very small distance. But what you have to bear in mind is, it's a small distance, but it's an awfully long way away. It's 200,000 light years away. So 4 minutes at that distance is a hell of a, you know, it's a hell of a fast way for a star to travel. It's a bit like the TGV of stars, I suppose, if you know your French trains. No, it's not just obscure stars that are runaway stars, but quite a lot of stars that you can see with the naked eye are too. Here, for instance, is Kappa Cas. It's obviously not part of the main W of Cassiopeia. It is one of the main stars in the constellation. If you think of the W, if you think you're writing the W with the pencil, then the sort of second V of the W, it should really be called double V, shouldn't it? Which is what they call it in French, double V. If you think you're writing the second V in that W, if you sort of flatten the V out, then Kappa Cas forms a sort of a trapezium at the top right. It's magnitude 4.2, so you know you can see it with the naked eye. And Cassiopeia, of course, is very close to the Milky Way. Being close to the Milky Way, there's lots of gas and dust floating around. And as Kappa Cas is coming in along this direction, it's flying through the sky, comparatively, obviously. And what it's doing is causing a bow shock in the nebular material here. Now, what that's going to do is interesting from my point of view, because it's going to compress the gas all around here, and that's going to start off even more star formation. So we've got more forming stars going on. And who knows, some of those forming stars might in turn produce other runaway stars. Now, just to look at another star here, this one is Zeta Ophiuchi, which is even brighter than Gamma Cas. It's one of the main stars in the sort of figure of Ophiuchus. It's magnitude 2, so easily visible with the naked eye. Ophiuchus is also quite close to the Milky Way, especially Zeta, which is in the southern bit of Ophiuchus. Again, near a very well-known and very active star-forming region. It's doing the same thing, but this time it's coming in along this direction probably, and it's causing a bow shock here. And tons of nebula here, so lots of stuff going on, lots of stars are going to be made here fairly soon. Just go on to the next one. This is one of the most famous runaway stars called PV Cephei. Now, this is a proper variable star, it really is. Just show you four different photographs of this object. If we could just first of all concentrate on this little sort of cross-shaped group stars here, that just helps you sort of, you know, realize what you're looking at. Because PV Cephei makes a triangle with these two. And they're also here, but you know, it's kind of laying on its side. You know, the camera's on its side. So this is in 1952, where we've got something doesn't actually look like a star. It looks more like a comet. It's quite possible that someone discovered a comet, in fact. But no, this is our forming star, PV Cephei. A few years later, well, quite a few years later, where's it gone? There's nothing there. Well, there's a smudge, isn't there? A very faint smudge of light. But if we look at that same area just 8 years later, it's the brightest star in the neighbourhood. PV-CVI is very, very variable. Here, its magnitude is 18. So, you know, you need a decent CCD to see it at all, really. And here, it's flared up to magnitude 11. So you can see it in a normal small telescope. So it's, you know, it's risen by 7 magnitudes. And if we just look a few years later here, it's still there, but it's obviously fading. And that's kind of where it is at the moment. And here you can see this cometary shape. It's a star in the process of formation. And what it's actually doing is it's expelling gas through its poles. That's what forming stars do. They draw gas in from the surrounding area. There comes a point when they can't take any more gas. So they have, the only thing really the gas can do is to escape through the points of least resistance, which are the poles of the star. Now, this is obviously coming out of one pole of the star. We can't see the other one because it's tilted away from us. Obviously, this, you know, this area of gas here is pointing slightly towards us. That's why we can see it. But you've got the forming star there, which isn't visible because it's not yet hot enough. And the gas and dust that's forming the star is obscuring the other, as it's called, bipolar outflow coming out of here. This is a really, really interesting object. It's one of these things that you have to keep looking at all the time because there's no telling what it's going to do and when it's going to do it. Right, now I just, at this point, this is quite a short talk, it's shorter than I normally do, so be thankful for that. I just want to go back actually to one of the pictures we were looking at earlier, and that is Orion. Now I said earlier that the supernova that happened about here, which I hope you will accept did actually happen from various bits of evidence that have shown, happened between 2 and 3 million years ago. It's fairly well established, I think, by now, that humanity, as we know it, to use that wonderful phrase, grew up, became Homo sapiens, roughly in the area of sort of equatorial Africa, Kenya, Tanzania, that sort of area. That's where all the earliest sort of bones have been found, on the borderline between Homo sapiens and the kind of whatever came before. Now, the interesting thing to notice about this is, where is Orion in the sky? Oh, I know, it's on the equator, isn't it? So, from Kenya, or the surrounding area, the supernova, when it went off, would have been directly overhead. So it wouldn't have had the light and the stuff coming off it. You know, it wouldn't have had to come through a thick layer of our atmosphere. It would have come straight down, you know, basically onto the head, if you think of it that way. And I'm just wondering, because of course we have seen supernovae before in our own galaxy. There was Tycho Brahe's supernova in 1572. Now we know that that was about 8,000 light years away. About 30 or 40 years after that, there was another supernova observed by another famous astronomer, Johannes Kepler, in 1604 in Ophiuchus. That's Ophiuchus again, you see. We know that that's even further away. That's about 24,000 light years away. But this one was a mere 1,000 light years away. Now, you have to bear in mind that when a star goes supernova, it's as bright, it's as luminous as all the other stars in the galaxy combined. So we're talking here of a star putting out, because it doesn't just put out visible light, it puts out high intensity radiation, which we know can affect human cells. That's why we wear sun cream, because of all the UV light coming off the sun. Now, I'm just wondering that along with all the light that's pouring off this thing, whether some of that very short wave radiation maybe might have had an effect on our evolution as a species. It's just something to think about. So I shall leave you pondering that philosophical question. And stop screen sharing. There we go.
Okay, Michael, that's a really interesting place to leave it.
Yes.
Thank you for a really interesting talk, and a subject that ties in so many of the different topics we usually approach separately, Runaway Stars. So, ladies and gents, we're looking for questions now, and as usual, a digital hand would be preferable to waving at me. But if you do wave, keep on waving, because I've got a couple of screens to look through. So, have we got any questions? I can't see anybody. Oh, Peter Lloyd. Thank you, Peter.
Yes, thank you, Michael. Very, very interesting talk. It was just a point that you brought up in one of your early slides when you were talking about how runaway stars might be created. You seem to be saying on the left-hand side that if you had a star rotating extremely fast, it might separate into two and throw one piece away. And this, of course, was an early theory about how the moon formed, and really is discredited because a fluid body simply wouldn't divide that way. It would shred a ring around the equator if it did anything like that at all. So I just wondered if that's what you were saying.
They're not really the same thing, because of course the Earth and Moon are solid bodies, whereas stars aren't, especially forming stars aren't.
Well, the Earth was thought to be fluid at the time.
Not as fluid as stars, I think you'll find.
All right.
I think the dynamics are all different.
Okay.
I think
Okay.
so.
Okay, Peter. Tony Morris, did I see your hand raised?
You did, Paul.
Okay.
Right. We're told that action and reaction are equal and opposite. So when we've seen you've demonstrated these stars flying off, have we got any objects that are flying in the opposite direction?
I'm not exactly sure what you mean. I mean, those three stars that I talked about, 53 Arietis, Aorgi, and New Columbi, are all flying in different directions.
Yeah. So like an artillery gun fires the shell, but the gun moves back. There's a recoil. So where those three stars set off from, is there something going in the sum of the opposite direction?
Well, I mean, it's one of the main problems is that is a very, very complicated part of the sky. You know, obviously Orion, it's full of nebula material. It's full of very, very massive stars, and obviously only very massive stars can go supernova. So that's what tends to make me think that it wasn't really a case of the stars, if you like, sort of coming out of the supernova. It was a supernova that provided the impetus for them to start flying away.
Right, okay.
This is an area where we don't really know very much, you know, because obviously it's only quite recently that we've had probes like Gaia that have been able to sort of demonstrate this. So it's kind of cutting edge, if you like, which is probably why I'm not sure as to the answers of a lot of the questions.
Okay. Okay, a second one then. You showed Gulbidarian's nebula.
Yeah.
Well, that's been an object of observation for the BAA Deep Sky section for a number of years.
Oh, really?
So they've got quite a history of amateur observations, especially in the UK. And a couple of years ago, I think Nick Hewitt gave a talk on the variability of the stars in that area.
Yeah.
And they were discussing the fact that it's not the star that's variable, it's the density of the molecular cloud that's around it that's variable.
what you have in these situations is a sort of an interplay between both of the objects, between the star and the interstellar medium. The actual view you get of Gilbert-Dagan's nebula is, I don't know if you remember the picture, but it's, you kind of get this brown gas, don't you? Apart from the other sort of nebulosity in the neighborhood. Of course, it's a bit like Orion. It's a very nebular part of the sky. It's full of nebulae, full of star-forming regions. But yes, I mean, really, it's a bit like the case that you get with Hubble's variable nebula, which is caused by another variable star called R Monocerotis. Well, it actually looks like PV-CVI as well. It's got this kind of triangular nebula coming out of it, which actually isn't a nebula. It's one of the bipolar outflows from the forming star. That's why a lot of these forming stars have these kind of triangular appendages to them, because they're not strictly nebulae, they're just stuff that's coming off the star. Obviously, it's a very young star, it's a forming star, so it is independently variable, which of course makes the nebula appear to vary as well. And the nebula really is varying. It's not just an apparent thing, because obviously the star is now interacting with the nebula as well. So yeah, it's a very dynamic part of the sky.
Yeah. So Gulbaderan's nebula went very dull for many years, and I think it was rediscovered by an American amateur with a 3-inch refractor.
Are you thinking of J. McNeil's nebula?
Yeah, is that the same area?
No, that's near the one he discovered is near the Horsehead Nebula, so completely the other side of the sky. It's in Orion.
Right. Okay. I thought it was a subsection of M78. I could be wrong.
Yes. Yeah, that's right. M78 is near the Horsehead Nebula.
Oh. Okay. It's just as you say, it's a very dynamic part of the sky.
It is. Yeah. Yeah.
Okay, thank you.
Okay, thank you, Tony. Galaxy Tab A7. Your question, please. Can we have your question, please?
Yeah, it's not really that long, but it's just a short one. How much times the mass would you say a star would need to be of the sun in order to go supernova? Like
stars that are at least about 9 times the mass of the sun. And when we say mass, all we really mean is how much stuff. All right. So a star has got to have at least 9 times more stuff in it than the sun has got. That's why the sun itself can't go supernova. It's not massive enough.
Okay.
So we're talking stars like Betelgeuse, Rigel, Deneb, a lot of the bright stars that you can see in the sky are bright simply because they're luminous, and they're luminous because they are massive and hot. That's why most of the Megabite stars are actually, in reality, they are brighter than the sun, because they're obviously a long way away, and the only way we can actually see them at the distances that they are at is because they're very luminous. So yeah, I mean, a star has to be at least sort of 9-10 times more massive than the sun is if it's going to go supernova, or it has to be a certain type of double star. And of course, the sun is a single star.
Okay, thumbs up if that's all right for an answer. 9 times as big as the sun. Excellent. Michael, you were talking about the plough. And at least 4 stars of the plough have got the same relative motion, and that indicates that they come from the same stellar nursery.
Yes.
Yeah. Have any stars been identified that may belong to stellar nursery that gave our sun?
Oh, that's an interesting one. Again, the answer is I don't know.
Oh, okay.
And it's basically the same reason. It's only within the past few years that we've actually been able to, determine all those parameters.
Yeah, I was just thinking that have have any stars been identified with actually no relative velocity to the sun? So those parameters would all be 0, wouldn't they?
Well, they might not be 0, but they would be very, very small, I suppose. Yeah.
Right.
The sun itself is moving in the general direction of, it's somewhere between Hercules and Vega. So we need it's at about 18 hours right ascension, about 25 degrees declination. So if we can find other stars that have got, you know, similar proper motion to that, then we can probably do some way to identify them. The difficult bit with that is, of course, you have to look 4.5 billion years back in time, or probably a little bit more, when the sun was actually born. So, you know, you've got a lot of catching up to do to trace the other stars, because since that time, the sun and obviously all the other stars have actually gone around the galaxy several times over. It takes the sun about 250 million years to go once around the galaxy. So, you know, the sun and all the other stars that presumably came from the same gas cloud where it was born, you know, they've all been going around the galaxy several times since they were born. So it's going to be a very, very difficult thing to do.
Okay, Roy Gunson, please.
Yeah, Michael's sort of half answered what I was going to say. I mean, but what I was going to say is that there were some reports that they'd looked at some stars that are similar composition to our sun, but they came up with the idea that they might have been born together. But then when they looked at the ages of the stars, that there was such a dissimilarity that they had to be discounted. So as far as I'm aware, we've not found anything. But going back to the stars of Ursa Major, there is actually a thing called the Ursa Major Moving Group, which is an awful lot of stars right across the sky, which are all moving in the same direction.
Yeah, that's what those 5 stars are a member of. And as I said, there's quite a lot of stars in the neighbouring constellation. Well, there are also other stars in the same group in Ursa Major. I think Theta Ursa Majoris is another one. There are quite a lot of stars in Lynx and Leo Minor as well. They're also part of the same group, and we've found lots of other moving groups. There's one in various southern constellations of Tucana and Horologium, you know, that are also in moving groups as well. So these things are flying all over the place.
Okay, so Catherine's just put up a note for those people who haven't seen it. And she writes, HD 162826 is considered to be a solar sibling. It's 110 light years away and is in the constellation of Hercules. It'll be interesting to see how they actually work that out. I shall have to read that. Thank you for that input, Catherine. Okay, so I think we've worked Michael hard enough this evening. Can we finish then tonight with a big Mexborough Swinton Astronomical Society? Thank you. Thank you very much, Michael, for an interesting talk.
Thank you. Thank you.